SwayamPrabha. Digital India. Educated India.
In today's lecture, we continue our discussion on velocity and acceleration analysis of planar mechanisms. To start with, we take up two examples. The first example will illustrate the use of the concept of velocity and acceleration image. The second example will illustrate the use of the concept of coincident points, that means instantaneously coincident points belonging to various links. So let me start with the first example. We take the example of a slider crank mechanism with O2A as the crank, AB as the connecting rod which is connected to the slider. Suppose the crank angular velocity is given as omega 2. Omega 2 is given. This is the fixed link number 1, the crank is link number 2, connecting rod is link number 3, and the slider is link number 4. We also assume that this omega 2 is constant. That means the angular acceleration alpha 2 is assumed to be 0. The question that is posed, that at this configuration find the point on the connecting rod that has 0 velocity. So the question is, find a point on the connecting rod that is link 3 which has 0 velocity. Let me call that point D. So VD is 0 and D is a point on link 3. To determine this, let me start with the velocity diagram which we have drawn earlier. Let the velocity of the point A, which is perpendicular to O2A, is drawn to a scale, and I represent it by small O2A. This is the velocity of the point A, which is completely known. VA is omega 2 cross vector O2A. Now we consider 2 points A and B belonging to the same digit body, namely 3. So we can write VB is VA plus omega 3 cross AB. As we said earlier, before trying to draw the velocity of B, let us verify that this vector equation does not have more than 2 unknowns. So for velocity of B is concerned, we know the direction, that is horizontal, but we do not as yet know the magnitude. Velocity of A has been completely determined and has also been drawn, so this is completely known. omega 3 cross AB is perpendicular to AB, so I know the direction of this vector, but I as yet do not know the magnitude. So this vector equation has two unknowns as represented by these two crosses. So this equation now can be drawn graphically. To satisfy this equation, because VB is horizontal, I draw a line horizontal and passing through O2. Now this vector omega 3 cross AB is perpendicular to AB. So through A I draw a line which is perpendicular to capital AB. And these two lines intersect at the point B. So this vector O2B represents the velocity of the point B, and this vector AB represents omega 3 cross AB. So this completes the velocity diagram, but the question, if we remember, that we want to find a point on link 3 which has zero velocity at this instant. That means we should find a point in the space diagram whose image is at O2. As we see link 3, there are 2 points A and B, which are corresponding points in the velocity diagram is small a and small b. So if to find the point D, this point D, whose image should be O2 such that velocity of D is 0. So what we do? As we see, this line is perpendicular to capital AB, this line is perpendicular to capital O2A. So let me call this angle phi 1 and this angle phi 2. Note the direction that the phi 1 is counterclockwise at A and phi 2 is counterclockwise at B. So here in the space diagram at capital AB, I draw a line at an angle phi 1 counterclockwise at A, and at B is clockwise, so I draw a line clockwise at an angle phi 2. And these two lines intersect at the point D. So what we see, that this figure capital DAB is similar to this figure O2AB. The image of the point A is small a, image of the point capital B is small b, and image of the capital point D is small O2. So this is the point D whose velocity is 0. At this instant, this point on the connecting rod has a 0 velocity. As we see, the angle between small ab and AO2 is phi 1, and AB is perpendicular to capital AB, and AO2 is perpendicular to O2A. That is why if this angle is phi 1, the angle between these two lines, if I extend it, also becomes phi 1. Now AB is perpendicular to AB and BD is perpendicular to O2B. So angle between them is phi 2. So the angle between them is also phi 2, because these two lines are respectively perpendicular to these two lines. At this stage, it is very easy to note that this point D is nothing but what we earlier called P13, that is the instantaneous center of body 3 with respect to body 1. The relative instantaneous center of body 3 with respect to body 1, that is the fixed link. Consequently, velocity of this point at this instant is 0. That this point is P13, I will ask the students to do it themselves using the Aronhold-Kennedy theorem of 3 centers, which we have discussed in detail in one of our earlier lectures. The next problem is to determine the point, say E, such E belonging to link 3 whose acceleration is 0 at this instant, we have to determine the point E. To determine the point E on link 3 which has 0 acceleration at this configuration, let me first carry out the acceleration analysis. As we see, the acceleration of the point A can be written as omega 2 squared AO2, vector AO2. So this is completely known because omega 2 is given and alpha 2 we have assumed to be 0. So I can draw the acceleration of the point A parallel to AO2 to some scale and mark the pole as O2 and this point as A. This is omega 2 squared AO2. Now we write the acceleration of the point B is acceleration of the point A plus omega 3 squared BA plus alpha 3 cross AB. So for acceleration of B is concerned, we do not know the magnitude, but I know the velocity which is horizontal. Acceleration of A is completely known and we have already drawn it here. From the velocity analysis, we have already determined omega 3, that is the angular velocity of link 3. So omega 3 is known, BA vector is known, so this is completely known. This vector omega 3 square BA. Alpha 3 cross AB, I know the direction because it is perpendicular to the vector AB, but I do not know the magnitude. So in this vector equation, again we have two crosses, so we can complete this vector equation in the diagram. First we draw omega 3 squared BA, that is parallel to this vector BA from A. Let it be so much to the same scale. This is omega 3 squared BA. Now alpha 3 cross AB will be perpendicular to this vector. So I draw a line which is perpendicular to this point. Let me call this point B prime. But AB is horizontal, so through O2 I draw a line horizontal, and where these two lines intersect gives me the point B, such that the vector O2B represents acceleration of the point B, O2A represents the acceleration of the point A, and B prime B, this vector represents alpha 3 cross AB. There is no need to repeat up to this point because this we have done earlier while analyzing the velocity and acceleration of a slider crank mechanism. Now let me try to answer this question E, such that acceleration of the point E is 0 at this configuration and the point E belongs to link 3. We have already got the figure, the image of the point A here as small a, image of the point B here as small b. So if I draw this line, then ABO2, if I draw a figure similar to this ABO2 with capital A and capital B representing the point small a and small b, wherever O2 goes, that point will be E, because then the acceleration of the point E will be 0. To locate that point E, we note that this angle is say psi 1 in the clockwise direction at A, and this angle at B is say psi 2. So at A, I draw a line at an angle psi 1 with AB. With AB, the point O2 is at an angle psi 1 at A. So with AB, I draw an angle in the clockwise direction and psi 1. So E must lie on this line. Similarly, at B, I draw a line which is almost 90 degree. So I draw a line which is at an angle psi 2. This angle is psi 2. At B, O2 lies on a line which is drawn at an angle psi 2 in the counterclockwise direction to AB. So here I draw at capital B a line which is oriented at an angle psi 2 in the clockwise direction from capital AB. The correspondence between the small letters and capital letters should be noted. Where these two lines intersect, that gives me the point E, such that image of the point E is O2, which means that the acceleration of the point E belonging to link 3 at this instant will be 0. It is needless to say that this point D with 0 velocity or this point E with 0 acceleration belonging to link 3 may lie outside the physical boundary of link 3. They belong to link 3 in the plane of motion of link 3, but they may exist outside the physical boundary of this link 3. So this is the point with 0 acceleration on link 3, this is the point with 0 velocity on link 3 at this particular configuration. So the use of the velocity and acceleration image of a particular link is shown through this example. In our next example, we consider a 4-link RP-RP mechanism and show the use of the instantaneously coincident points belonging to different links, how these could be used for velocity and acceleration analysis. This is an RP-RP mechanism. Link number 1 is connected to link number 2 through a revolute pair. Link number 2 is connected to link number 3 through a prismatic pair. Link number 3 is connected to the slider, which is link number 4 through a revolute pair, and link number 1 and 4 are connected by a prismatic pair. The problem is as follows. Suppose we are given the input motion omega 2. I take some numerical values. Say omega 2 is 2 radian per second in the counterclockwise direction. And angular acceleration of the link 2 at this instant, say alpha 2, this is omega 2. Alpha 2 is also given as 4 radian per second squared. The statement of the problem is determine with these input velocities and acceleration at this configuration what is the velocity of the slider 4 and acceleration of the slider 4. So let me first carry out the velocity analysis, and we are given, suppose this distance at this configuration is, I take another numerical value, is say 5 centimeter. To carry out the velocity analysis, I consider instantaneously coincident points at this revolute axis of the block center and call it P3, which is always coincident with P4. There is no relative movement between these two coincident points P3 and P4, P3 belonging to link 3 and P4 belonging to link 4. But I also consider a point P2 which belongs to link 2 but at this instant coincident with P3 and P4. Now let us see whether we know the path of the point P4 in link 2. It is needless to say, because P3 and P4 are always coincident, path of P4 on 2 will be same as the path of P3 on link 2. To judge the path of P3 on link 2, what we do, we hold imaginarily link 2 fixed and try to move link 3. If we try to move link 3, it is obvious that because of this slider, 3 can only go in the vertical direction on link 2. So the path of P3 on 2 is this vertical line given by this vertical line. This is the path. This is the path of P3, which is same as P4 on link 2. Now we can write that velocity of P4 is velocity of P2 plus velocity of P4 on link 2. This relation we have derived earlier between coincident points belonging to two different links 2 and 4. Vp4 is Vp2 plus V4 as seen by an observer on link 2. Now what we see, that velocity of P4 has to be horizontal because of this prismatic pair in the horizontal direction between 4 and 1. All the points on link 4 must move horizontally. So I know the direction of Vp4, which is horizontal, but the magnitude is unknown. Now velocity of P2 I can write, because omega 2 is given, it is omega 2 cross O2 P2. The vector O2 P2 is known, it is 5 centimeter in length and along the horizontal direction. Omega 2 is 2 radians per second in the counterclockwise direction. So the velocity of P2 is completely known. So I know the magnitude and direction. What is the magnitude? Omega 2 is 2, O2 P2 is 5. So the magnitude is 10 centimeter per second, and because of this counterclockwise omega 2, the velocity of P2 is in the vertically upward direction. So I can draw velocity of P2 which is vertically up, and let me represent it as O2 P2. Now what is the velocity of P4 on 2? Because the path is vertical, that means velocity which is tangential to the path must also be vertical. So I know the direction, but we do not know the magnitude. So again in this vector equation there are two crosses, so I can draw it. I have already drawn Vp2 by O2 P2, and Vp4 is also vertical. But how about Vp4, which is horizontal? So two vertical vectors giving rise to a horizontal resultant vector implies that this vector must be of 0 length. So if I draw this vertical, I am drawing it intentionally a little to the left, a little to the right. Actually it is lying on the same line. This is vertical, and these two vectors put together must give me P4, and O2 P4, which is of 0 length, represents the velocity of the point P4. So two vertical vectors, resultant of that is horizontal, implies this vector must be of 0 length. So velocity of P4 at this particular configuration is 0. That means this block is momentarily at rest. And what is Vp42? As this diagram shows, this vector and this vector of equal length such that P4 becomes coincident with O2. So this I get just as Vp2 magnitude, which is 10 centimeter per second, but in the vertically downward direction. Now that we have completed the velocity analysis of this mechanism, let me start with the acceleration analysis. From the velocity analysis, we have already obtained that Vp4 is 0, whereas Vp4 on 2 is 10 centimeter per second in the vertically downward direction. To carry out the acceleration analysis, we write AP4 is AP2, that is the coincident point, plus AP4 as seen by an observer on 2, which I write as AP42, plus the Coriolis acceleration, which in this case is twice omega 2 cross Vp42. P2 and P4 are coincident points belonging to link 4 and P2 to link 2. From this acceleration equation, let me determine which velocities, which vectors are known and which vectors are unknown. AP2 is completely known because the input angular velocity omega 2 and input angular acceleration alpha 2 are prescribed. So I can write AP2 is omega 2 squared P2O2 plus alpha 2 cross O2 P2. Everything is specified, so AP2 is completely known. Magnitude of omega 2 squared P2O2 is omega 2 squared is 2 squared, that is 4, P2O2 is 5, so this is 20 centimeter per second squared. The magnitude of omega 2 squared into P2O2, this vector is 4 into 5, that is 20 centimeter per second squared, and the direction is along the vector P2O2, that is horizontal to the left. Alpha 2 cross O2 P2. O2 P2 is 5 centimeter and alpha 2 is 4 radians per second square. So the magnitude of this is also 4 into 5, is again 20 centimeter per second square. Same magnitude, 20 centimeter per second square. And what is the direction? Alpha 2 is clockwise, so the transverse acceleration is vertically in the downward direction. So this vector is completely known. How about AP42? The path of P4 on body 2, as we have seen, is this vertical line. So the direction of this vector is completely known. This is along a vertical line, but the magnitude is unknown. We have already determined Vp42 as 10 centimeter per second in the downward direction, and omega 2 is given to be 2 radians per second in the counterclockwise direction. So this vector, both the magnitude and the direction is known. There are AP4, I know the direction, that is horizontal, and magnitude is unknown. So in this vector equation, again we have only 2 crosses left, so this vector equation can be represented by a vector diagram. Let me try to draw this vector diagram. AP2, I write omega 2 squared O2 P2 to some scale. Let me say this is O2. This point I call P2 prime, because this is only this component, which is 20 centimeter per second square to the left. Then this component is again 20 centimeter per second square, but in the vertically downward direction. So I draw again of the same length, and this is P2. This is alpha 2 cross O2 P2, and this vector is omega 2 squared into P2O2. Now this vector is completely known, so let me try to draw this vector at P2. Vp42 was 10, omega 2 is 2, so 2 into 2, 4 into 10, 40 centimeter per second squared, and it is in the horizontal direction, but double of this length. This is 40 centimeter per second squared, and this vector represents twice omega 2 cross Vp42. And AP42 I know is vertical, so I draw a vertical line through this point. This was horizontal, so it is a 90 degree, and these four vectors, these two vectors represent this vector represents this, and this vector is in the vertical direction, and all these three vectors summed over must give me AP4, which is horizontal. So I draw a line horizontal, and wherever they intersects, that gives me the point P4. According to this vector equation, this O2 P4 represents acceleration of P4, and this represents acceleration of P4 as seen by an observer on body 2. So this diagram represents this vector equation, and it is easy to see because this is 40 horizontal line, this is 20 which is also horizontal line, so this must be 20. So AP4 I get as an answer is 20 centimeter per second squared in the horizontal direction from left to right. So this example clearly shows the power of considering the instantaneously coincident points on various links when we have sliding joints on rotating links. Now that we have completed velocity and acceleration analysis by graphical method, let me show you how to carry out this such velocity and acceleration analysis through analytical method. In analytical method, just as in the displacement analysis, we start with the loop closure equation. That means we represent the link lengths and sliding displacement as vector quantities and go through each loop that is present in the mechanism and write the corresponding loop closure equation in terms of these vectors. The first step for carrying out the velocity and acceleration analysis is obviously to complete the displacement analysis. Now that this loop closure equation is valid for all instants of time, we can differentiate both sides of such loop closure equations to complete the velocity and acceleration analysis. Successive differentiation of this loop closure equation with respect to time will give us the required velocity and acceleration relationships. I would like to mention one point here, that in the displacement analysis through analytical method, we always get nonlinear algebraic equation. Whereas if the displacement analysis is complete, which is always necessary to carry out the velocity and acceleration analysis, for velocity and acceleration analysis, we always get linear equations in the unknowns. That means the problem is much simpler. As an example, let me start with a 4R linkage. That means 4 links connected by 4 revolute joints. Let us look at the diagram of these 4R linkages, namely O2, A, B, O4. As in the displacement analysis, we set up a coordinate system, Cartesian coordinate system, xy, with the origin at the revolute pair O2. The fixed link is represented by O4, O2, the interlink by O2A, the coupler by AB, and the follower or the output link by O4B. For this given configuration, that is, if theta 2 is given, by displacement analysis we can obtain theta 3 and theta 4. After doing this displacement analysis, that is, knowing theta 3 and theta 4, we should be in a position to carry out the velocity analysis. What do you mean by velocity analysis? Let us say the input velocity, that is theta 2 dot, the angular velocity of link 2 is prescribed, and we have to find out the angular velocities of link 3 and link 4, which are given by theta 3 dot and theta 4 dot respectively. Obviously, everything is measured positive in the counterclockwise direction. So let me write now the loop closure equation. Vector L1 plus vector L2 plus vector L3 is vector L4. This is exactly the same as we did in the displacement analysis. So let me write now these two-dimensional vectors in terms of complex exponential notation, that is L1 plus L2 e to the power I theta 2. The vector L2 can be represented by this complex exponential notation. Magnitude is L2 and the orientation of this vector with the positive x-axis is given by theta 2. Similarly, L3 vector is L3 e to the power I theta 3 is equal to L4 e to the power I theta 4. As we know, e to the power I theta can always be written as cos theta plus I sin theta. So what we say, we equate the real and imaginary parts of this particular complex equation, which is same as saying equating the x component and y component of two sides of this vector equation. That way we get L1 plus L2 cosine theta 2 plus L3 cosine theta 3 is L4 cosine theta 4. Equating the imaginary parts, we get L2 sin theta 2 plus L3 sin theta 3 is L4 sin theta 4. So this complex equation is equivalent to two real equations, which I mark as equation number 1 and 2. Now these equations are valid for all instants of time where theta 2, theta 3 and theta 4 are functions of time, whereas the link lengths L1, L2, L3, L4 are constants, time independent constants. Because these equations are valid for all instants of time, I can differentiate both sides of these two equations with respect to time, and I can write from the first equation L2 sin theta 2 dot, I am differentiating with respect to time, plus L3 sin theta 3 dot is equal to L4 sin theta 4 dot. Similarly, from the second equation I get L2 cosine theta 2 dot plus L3 cosine theta 3 into theta 3 dot is equal to L4 cosine theta 4 into theta 4 dot. So we have two equations where, because the displacement analysis has been completed, I know the values for given values of theta 2, the value of theta 3 and theta 4. The input angular velocity theta 2 dot is given, and our objective is to determine the two unknown angular velocities theta 3 dot for the coupler and theta 4 dot for the output link. The thing to note that these two equations in these two unknowns theta 3 dot and theta 4 dot are linear, so we can easily solve for these two unknowns from these two linear algebraic equations. To eliminate say theta 4 dot, I multiply this equation, let me call it number 3, and this equation if I call number 4. If I multiply equation 3 by cosine theta 4 and equation 4 by sine theta 4 and subtract, then I get the right hand side 0. So what we have done? We have multiplied by cosine theta 4, the top equation. So I get L2 theta 2 dot sine theta 2 cosine theta 4 minus cosine theta 2 sine theta 4, which gives me sine theta 2 minus theta 4. And here I have multiplied by cos theta 4, and here I have multiplied by sine theta 4 and subtracted. So I get L3 theta 3 dot sine of theta 3 minus theta 4, and this is equal to 0. Let me check. Sine theta 2 cos theta 4 minus cos theta 2 sine theta 4, sine theta 3 cos theta 4 minus cos theta 3 sine theta 4. So I have eliminated theta 4 dot from these two equations, and I can obtain the unknown theta 3 dot as minus L2 by L3 sine of theta 2 minus theta 4 divided by sine of theta 3 minus theta 4 into theta 2 dot. So if the input angular velocity theta 2 dot is given, and we have carried out the displacement analysis such that the values of theta 2, theta 3 and theta 4 are known, I can easily find out the angular velocity of the coupler theta 3 dot. If it turns out to be positive, then theta 3 dot is counterclockwise. If it is negative, then theta 3 dot is clockwise. Similarly, I could have eliminated theta 3 dot from these two equations, and we obtain theta 4 dot. That I leave for the students to carry out as an exercise and complete the velocity analysis. Next, let us see, starting from these two equations 3 and 4, how can we carry out the acceleration analysis. To carry out the acceleration analysis, let me start with these two velocity equations which we have numbered as 3 and 4. These two velocity equations are also valid for all instants of time. So I can again differentiate these two equations with respect to time and maintain this equality sign. So let me differentiate the first equation, then I get L2 cosine theta 2 dot squared plus L2 sine theta 2 into theta 2 double dot. These two terms I get from the first term if I differentiate with respect to time. Similarly, differentiating this term with respect to time, I get two more terms, namely L3 cosine theta 3 dot squared plus L3 sine theta 3 double dot, and that is equal to, again differentiate the right hand side, I get L4 cosine theta 4 dot squared plus L4 sine theta 4 double dot. This is one acceleration relationship. This equation let me number as phi. Similarly, from the second equation I get minus L2 sine theta 2 dot squared plus L2 cosine theta 2 double dot. These two terms I get by differentiating this first term with respect to time. From the next term I get two more terms, namely minus L3 sin theta 3 dot squared plus L3 cosine theta 3 double dot, and that is equal to, differentiating the right hand side with respect to time, I get minus L4 sin theta 4 dot squared plus L4 cosine theta 4 double dot. Let me call this as equation 6. Since the velocity analysis has already been completed, now theta 2 dot, theta 3 dot and theta 4 dot, these are all known. The input angular acceleration theta 2 double dot has been prescribed, and our objective is to obtain the two unknown acceleration theta 3 double dot, that is of the coupler, and theta 4 double dot, that is of the output link. So these two equations 5 and 6 are again two linear simultaneous equations in two unknowns, namely theta 3 double dot and theta 4 double dot, and it is very easy to solve these two unknowns, and I leave the students to complete the algebra and find out theta 3 double dot and theta 4 double dot in terms of theta 2, theta 3, theta 4, which have been obtained from the displacement analysis. This is prescribed. These two have been obtained from the displacement analysis. Theta 2 dot, which has been prescribed, and we have already obtained theta 3 dot and theta 4 dot from the velocity analysis, and the input angular acceleration theta 2 double dot. Exactly the same way we eliminate theta 4 double dot to solve for theta 3 double dot, and then we eliminate theta 3 double dot to obtain theta 4 double dot, which will be again functions of all these variables. That completes the acceleration analysis by analytical method. So, at the end of this lecture, we have completed our discussion on velocity, on acceleration analysis of planar linkages, both by graphical method and analytical method.